Let's look at how to perform differentiation of hyperbolic functions. Examples of hyperbolic functions are as follows: hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic secant, hyperbolic cosecant, and so on. Two of the most basic hyperbolic functions are hyperbolic sine and hyperbolic cosine. Hyperbolic sine can be expressed in terms of exponential functions as follows. It is e to the power x minus e to the power minus x over 2. Hyperbolic cosine can also similarly be expressed in terms of exponential functions. And the definition is like that. Note the difference in the signs of these two hyperbolic functions. So let's start by differentiating hyperbolic sine of x. Now we know from this definition, hyperbolic sine of x is quite simply exponent to the power x minus exponent to the power minus x divided by 2. The half can be taken out. Differentiating e to the power x will give you e to the power x, as we have discussed before. Differentiating e to the power minus x will give you minus 1 e to the power minus x, and this is half e to the power x plus e to the power minus x, which is just this, which in fact is hyperbolic cosine of x. Likewise, to differentiate hyperbolic cosine of x, you use this definition. So as before, you can take that half out. Now differentiating e to the power x, you get e to the power x. Differentiating e to the power minus x, you get minus e to the power minus x. And this is hyperbolic sine of x. So when you differentiate hyperbolic cosine of x, you get hyperbolic sine of x. What about hyperbolic tangent? How do you differentiate hyperbolic tangent? Now the definition of hyperbolic tangent is hyperbolic sine over hyperbolic of cosine. So the dy dx can be obtained using the quotient rule. You differentiate the top one, and that's going to give you hyperbolic cosine of x. Multiply the denominator, another hyperbolic cosine. Subtract, now differentiate the denominator. You will get hyperbolic sine of x times the numerator. You get hyperbolic sine of x. Divide by the square of the denominator. Square of hyperbolic cosine of x. So the square of hyperbolic cosine minus the square of hyperbolic sine is just 1. That is just the identity. So divide that by hyperbolic cosine x squared. You get 1 over hyperbolic cosine of x squared. And that is just hyperbolic secant x squared. And that's the answer. Let's look at this function, hyperbolic secant of x, or 1 over hyperbolic cosine of x. So we can use the quotient rule again here. Differentiating the top, you get 0. Minus, now differentiate the bottom, you get hyperbolic sine of x. You multiply with the 1 on top, which is 1. Divide by the square of the bottom, which is hyperbolic cosine of x squared. And the answer is minus hyperbolic tangent of x times hyperbolic secant of x. Let's look at the following function. Now you have a power. The power is 2. So we can use differentiating function of a function technique. We can take g to be hyperbolic of sine, of x. So your y is just g squared. So dy dx is dy dg times dg dx. dy dg is just 2g, that's from here. dg dx is just the hyperbolic cosine of x. Now putting back the expression for g, you get 2 hyperbolic sine of x, hyperbolic cosine of x, which is just hyperbolic sine of 2x. That's from the identity. What about this one? To differentiate y with respect to x, let's substitute again h to be hyperbolic tangent of x. So dy dx is dy dh dh dx. dy dh, because now your y is h squared, will be 2h, and dh dx is hyperbolic secant x squared. Putting back the h, you get 2 hyperbolic tangent of x times hyperbolic secant of x squared. And that's the result. The following function has natural logarithm in addition to hyperbolic cosine. So let's first define a function g to be hyperbolic cosine of x. So that means in terms of g, your y is natural log of g. So when you calculate dy dx, you can use function of a function method, dy dg times dg dx. Now dy dg is 1 over g. That's what you get by differentiating natural log of g with respect to g. dg dx is just hyperbolic sine of x. Substituting the g inside, you get hyperbolic tangent of x, and that's the answer. What about this one? Now n is a constant, so let's define a function h, for example, as n times x. So your y in terms of h is hyperbolic sine of h. So that means your dy dx is dy dh times dh dx. Now dy dh from here is hyperbolic cosine of h. dh dx from here is just the constant n. So putting everything together, you get constant n times hyperbolic cosine of nx. I'm putting back h in terms of x here, and that's the final answer. Let's try to differentiate this function. Y is natural log of hyperbolic tangent of x. So let's take hyperbolic tangent of x to be a function g. Let's call it g. So your y in terms of g is natural log of g. So dy dx is dy dg times dg dx. Now dy dg from here is 1 over g, and dg dx from there we have shown earlier to be hyperbolic secant x squared. Putting back the g inside, you get 1 over hyperbolic tangent of x times hyperbolic secant of x squared. Hyperbolic tangent is hyperbolic sine over hyperbolic cosine. So 1 over hyperbolic tangent is hyperbolic cosine over hyperbolic sine times hyperbolic secant squared is 1 over hyperbolic cosine x squared. So you see that this will take away one of the hyperbolic cosine, And that's going to give you dy dx as 1 over hyperbolic sine of x times hyperbolic cosine of x. Using the following identity, 2 times hyperbolic sine of x times hyperbolic cosine of x being equal to hyperbolic sine of 2x, in here you will get your dy dx to be 1 over half hyperbolic sine of 2x, which can be reduced into 2 over hyperbolic sine of 2x, or quite simply 2 times hyperbolic cosecant of 2x. And that's the final answer. This function has inverse tangent in it, in addition to hyperbolic tangent as the argument of that inverse tangent. So of course we can apply differentiating function of a function method. So let's first introduce function f as hyperbolic tangent of x over 2. So that means your y in terms of f is just inverse tangent of f. So dy dx is dy df times df dx. Now dy df, we know from our previous videos, is 1 over 1 plus f squared. Remember, d over dx inverse tangent of x is 1 over 1 plus x squared. That's what we have used here. df dx can be easily found by first differentiating the argument x over 2 with respect to x, and that's going to give you 1/2, and then differentiating the hyperbolic tangent function itself, and that's going to give you the square of hyperbolic secant, like that. So putting everything together, you have hyperbolic secant x over 2 squared over 2. Now we know what f is. F is hyperbolic tangent x over 2. So the square of that is that. Now let's substitute hyperbolic tangent in terms of ratio of hyperbolic sine and hyperbolic cosine. So that's going to be hyperbolic secant x over 2 squared over 2 times 1 plus hyperbolic sine x over 2 squared over hyperbolic cosine x over 2 squared. So let's make the denominator of this term the same. So the top remains, the bottom, this is hyperbolic cosine, so let's make the denominator the same, plus hyperbolic sine x over 2 squared over hyperbolic cosine x over 2 squared. You see that this will go up and cancel the hyperbolic secant x over 2 squared, like this. And the denominator is just 2 cosine x, hyperbolic cosine x over 2 squared plus hyperbolic sine x over 2 squared. So the top is just 1. From the hyperbolic function identity, the bottom is just hyperbolic cosine of x, excluding the 2. So overall you have 1 over 2 hyperbolic cosine of x, or quite simply half hyperbolic secant of x. And that's the final answer. Thanks for watching.